I want to introduce potentially our youngest speaker at Director's Lunch, but by no means our least experienced. Blake is a member of the Astronomical Society of Victoria and has been I want to say a legitimate professional astronomer now for a year or two, and we're going to hear about his optical spectroscopic work today. I had hoped we would also hear about his work creating and using a radio telescope, and indeed connecting this up as part of an interferometer across Australia as part of the Jove system. He assures me that is imminent, but it didn't quite manage to have this work and the radio telescope all completed while he was getting famous, sitting on ABC Melbourne, so statewide broadcast, and also hosting a star party that made his school part of the successful world record attempt at stargazing live. And his event had 4 times as many attend. It's not a competition, but I lost at the CSIRO Parkes Radio Telescope. So Blake has, through his efforts in his school alone, as well as all of his other communication efforts online, has now meant that 70 students who previously did not have telescopes in his school now do. That is about half of his school have been changed by just this one action. And with a career, I suspect, and I very much hope, continuing for many decades to come in astronomy, I can't wait to see what he does next. But for now, we're going to hear about his research in optical spectroscopy. Would you please welcome to today.
Unfortunately, Ellen has taken off the first part of my
I cheated, I looked at your notes.
So I'm Blake. I'm part of the Astronomical Society of Victoria, as Alan said. I go to Melbourne Montessori School. And today I'd like to present to you my project on spectroscopy. Spectroscopy is the visualization of a white light split through a prism into the rainbow of colours: red, orange, yellow, green, blue, indigo, and violet. It was discovered by Athanasius Kircher, seen here, who coincidentally passed away 326 years before I was born. Exact to the day. I'd like to teach you what spectroscopy can be used for and show my observations of 5 different stars and their absorption spectra. So when you look at the night sky, you may notice some stars are a bit red or a bit blue, or a bit brighter or dimmer than others. So all stars are different, like us humans, and they're all at different phases of their lifetime. As stars convert energy, it alters their chemical composition and temperature, brightness and colour, therefore changing their classification. This Hertzsprung-Russell diagram shows you stars of different temperatures and brightness and how they are classified. The hotter stars are up the top, and the hotter stars are to the left and the brighter stars are up the top. Blue stars are hotter, whereas red stars are cooler. As you can see, a reference in my pun down the bottom. So absorption lines are a visual representation of light disturbed by a gas. The absorption lines create a set of fingerprints unique to each element within the periodic table. Therefore, by using spectroscopy on stars, we are able to figure out which elements are contained within a star. Spectroscopy can help us understand a lot about stars. A star's age is determined by looking at the amount of matter made up of the chemical elements, excluding hydrogen and helium. We can tell a star's temperature by the amount of hydrogen absorption lines in each star spectrum. For surface gravity, we look at the width of spectral lines. The wider the line, the higher a star's surface temperature. Surface gravity, sorry. The narrower the lines, the lower a star's surface gravity. For the mass of a star, it is best to look at a binary star spectrum, as the red and blue shift of the binary stars help us work out the velocity which is needed in the calculation of mass. I wanted to learn about the chemical compositions of stars, so I borrowed some equipment and got to work. I used an 8-inch Meade LX90 telescope, a Canon 450D DSLR camera, and a star analyzer grating lens. I also needed some software called RSpec to analyse the spectrum. So I connected the camera up to the grating and then attached those to the telescope, searched for each star, and then took my images. I had to play around with different exposure lengths and ISO settings until I got the best picture. I then processed these images through RSpec. I had to insert the image into RSpec, then rotate the image so that it's almost perfectly straight, and then made it fit between the orange lines that you can see on the screen down the bottom picture. Only the data between the orange lines are used when a program analyzes the data and creates a graph. Next, I opened the calibration wizard and used the synthesize tool. Once I calibrated the graph, it added colour from the spectra to the graph where it needed to be. I checked that my calibration was correct by seeing where the hydrogen bar lines were. I then looked for particular elements in the data. RSpec showed me the elements in the target stars. Looking at the data for each of the stars, you can see how their composition varies. Here you can see the spectra of 5 different stars that I observed in images. From top to bottom, it is Acrux, Betelgeuse, Canopus, Rigel Kentaurus, and Sirius. Acrux is a blue subgiant. It is the 14th brightest star in the night sky. Its main elements are hydrogen, sodium, calcium, magnesium, krypton, and iron. The following slides contain the data that I processed through RSpec. Betelgeuse is a red supergiant which is easy to spot with the naked eye because of its distinctive orange and red colour. Its main elements are argon, hydrogen, sodium, calcium, and krypton. Canopus is a supergiant star and the second brightest star in the night sky. Its main elements are argon, calcium, sodium, iron, magnesium, and krypton.
Look through for you.
Rigel Kentaurus is the third brightest star in the night sky. It is part of a triple star system and its main elements are argon, sodium, iron, magnesium, and krypton. Sirius A is almost twice as bright as Canopus. Its main elements are hydrogen, argon, sodium, iron, magnesium, and krypton. I found out that you can use spectroscopy on things other than stars, such as planets. Here you can see me showing the public the spectrum of Jupiter at the Stargazing Live event at Fed Square last year. And here is the data from the spectral image I took of Jupiter. It is mostly made up of hydrogen and helium. This project has brought together two of my favourite subjects, astronomy and chemistry. I had a lot of fun experimenting with spectroscopy, and I can't wait to experiment further and learn more. I'd like to learn how to use RSpec in more detail so that I can use spectroscopy to find exoplanets. Next time you're outside, and have a look up at the sky and try to see the different colours of the stars. Some are really cool.
Did you want to thank anybody before we got to questions?
I'd like to thank Mike over there, Chris Rudge, who is seen in this image here, who runs the junior section of the Astronomical Society of Victoria. I'd like to also thank my family for helping me with this project, and I'd like to also thank Rebecca for inviting me here today to speak to you all.
An astronomer that shows you how they fit all the data, a rare person. So I would like to open up just for a few minutes some questions for Blake, if you have a question. Ned?
This is amazing. Have you thought about going after maybe one or two of the bright galaxies you can see in the south? So I just had a quick look, and I think you could maybe hit Centaurus A or the southern Pinwheel galaxy. Because what you could try and do is you could see if you could measure how fast it's spinning. Be really fun.
I'll definitely have a think about that.
Darren?
So how long did you have to expose for to get the spectra at a reasonable signal to noise?
Well, most of the time it was between for the dimmer stars like A-Crux and Betelgeuse. I had an exposure of around about 30 seconds, but for the brighter stars like Canopus and Sirius, it was around 15-20 seconds.
So what sites or where do you go to usually do this observing? Or is
So there's a dark sky site owned by the ASB that's just north of Heathcote near Ladies Pass.
and your telescope is a 10-inch?
It's an 8-inch.
8-inch.
8-inch me.
A little bit about the radio project that Alan briefly mentioned before you got rolling.
Yeah.
So at the moment I'm building a radio dish. I'm building a radio dish made out of an old Foxtel dish from my grandparents' roof. So I'm just starting to wire it up. All I've got to do is get a couple of components, and then I should get us to solder it together on a circuit board, build a box around it, and it should be working.
Once it's working, what do you want to do with it?
Well, I'm planning to look at this, to look at the sound of that one. I'm also planning on after that building a Job radio on the roof of my house, and hooking it up with another Job radio on a friend's house and one at the dark sky site that I mentioned earlier.
Any other questions for Blake? I think we're all just like stunned. So, yeah, everyone will just...
How much do you want to come work with me?
Yeah.
Name your price.
Don't commit to
Can you point your radio telescope, or do you just have to watch things go by?
I can turn it 360 degrees, and I've also got about maybe 50-degree vertical tilt. Yeah.
And what frequency are you going to operate at?
I'm not sure of that yet. But,
we haven't got to that point just yet.
We can probably give you an antenna. You want to operate 40 megahertz.
All right. Let's, yeah, go ahead.
Do you have a website that you might?
Yeah, do you want to point us to a website?
There's a pen there, Blake.
Yeah, here, right behind you.
yeah, that's right.